Hey friends, welcome to a new episode of Calculuscious Explains It All with me, Calculuscious, aka Mathy Kathy, in a new setting today. I'm in my classroom. I'm really excited to be here. As you can see, I actually tried to decorate a little bit, which is much more than I usually do. But I'm going to warn you that you might hear some random bells go off throughout this video because for some reason random bells are happening. You know, like the bells to indicate change in class periods. Yeah, so we're just going to go with it. I'm not even going to edit it out. We're just going to deal with it. Okay. One more thing. I'm very proud of my decorations here, but as you can see, there's like little clips that are like, there's nothing on them yet. My vision for this is to get a Polaroid camera and just randomly throughout the year take pictures of really random things. It doesn't even matter what, as long as it, is like something funny or cool, and put them up here so that at the end of the year, there's all these little Polaroid pictures that sort of tell like a little tale of the year. But my problem is that I looked up how much Polaroid cameras cost, and no, I'm not going to do that right now because I've already spent a ton of money on other stuff. So eventually I'll get there, and this will be a really cute little backdrop for me, hopefully. All right, in this episode, we are going to discuss differentiability. Differentiability. Let's go with differentiability. Yeah. All right. I have a funny story about why I've decided to do a video just on this word. A few years ago, I decided to start doing quick quizzes. And a quick quiz is just a little quiz on one section, and it is used as like a tiny formative assessment for me and the students to make sure that they are understanding the concepts in a section before moving on. And the year that I started doing these quick quizzes, I gave one on like beginning derivative stuff, and the word differentiable was in there. And I noticed that like a lot of my students weren't showing that they were understanding what the word differentiable meant. And I was kind of bummed about it. And I remember mentioning it to one of my colleagues. I said, I gave this quick quiz. A lot of my students didn't know what the word differentiable meant. I really need to do a better job at, teaching that vocabulary to them. Well, it just so happens that quite a few students in the class were football players, and the colleague that I mentioned this to was one of their coaches. So he like drilled them on the word differentiable for like an entire week while they were practicing on the field. And needless to say, they definitely knew what the word meant by the end of that week. Another quick story. Oh, I just lost it. There it is. Okay. And it's what like inspired this meme is that I think this just happened like last year where, okay, so after giving that quick quiz and realizing that students didn't know what the word differentiable was, I worked for a couple years on, getting better at teaching vocabulary to my calculus students. And in particular, this word always stood out to me as one that I really needed to do a good job with teaching to my students. Anyway, I think I did a pretty good job last year of teaching what the word differentiable meant. But I remember one student in particular being absent when we were going over that lesson. And when he returned the next day, just feeling like this meme. And I made this meme after hearing the quote that I have at the bottom that's in my caption. It's an actual quote from my classroom. So I overheard a student say, "All right, Connor, I would probably think that this stuff is easy too, but I have no idea what the word differentiable means." So, and I was like, yeah, I'm going to make a meme from that. So I guess it was a pretty relatable one too. Look at that. Yay. All right, enough with the stories. Let's actually start to talk about what this word means. To be honest, I just before, preparing this video, or as I was preparing this video, I Googled differentiability because I was like, is that actually even a word, differentiability, or am I making that up? I don't typically use the word differentiability. I say, a function is differentiable or a function is not differentiable. Or whenever you see theorems in calculus, often you'll see that word differentiable in the theorem. So it turns out differentiability is a word. And in Wikipedia, here's what it says about differentiability of functions. So I think this is beautiful. This just looks amazing. And, maybe if you're like a hardcore math nerd, you agree. But for most students, they look at this and they're like, and what? And what? What is this telling me? Nothing, right? Like, this is not very helpful for students who are just trying to actually learn what stuff means. So in this video, what I want to do is I want to talk about what does differentiable mean? When it says, let a function be differentiable, or if a function is differentiable, when you see that wording in a theorem, what does it mean? Because it is actually pretty important to know. The way that I like to start to teach differentiability, or how to determine if a function is differentiable, is with a cute little exploration where we start with like a really basic function like y equals x squared, and we do what's called zooming in on a point. I'm going to click here and hopefully this works. Takes us to a site where we can do just a little bit of the exploration that I typically do in class. Like, I typically do this with a lot of different functions, but here we're just going to do it with one, to keep it quick. Okay, so what we're looking at is the function f of x equals x squared. I'm going to move my slider here to be at, I just lost it, a equals 2. Okay, sorry, I just had to pause. A student showed up, so I had to help them. All right, anyway, I have my point centered at 2, 4, right? If we're working with the function x squared, 2 squared is 4. And what I can do now is slide the scale factor, and what you want to watch is the second screen over here. Notice that it's zooming in. And it doesn't take very long for zooming in on this function to change the curve of y equals x squared into a straight line, right? And if you can do that, if you can zoom in on one particular point of a function, and what you end up seeing is a nice straight line that we could calculate the slope of. Typically, I actually make my students calculate the slope of these lines when they zoom in. That's what it means for a function to be differentiable at a particular point. Okay, if you can do that for every point along the graph of the function, then you would say that the function is differentiable everywhere. So that's like a really basic way to introduce what a function being differentiable means. This is one of my favorite activities that I usually do with my students, because they can very easily zoom in, they can see it, and what they're actually looking at here, what I tell them eventually is, what you're looking at is what the tangent line would look at for this, this point on the graph of y equals x squared. And so we do that, and at this point, students have an idea that there are shortcuts to use to find derivatives instead of using the definition. And, they start to actually realize what they are if they haven't by the time we get to this activity. So it's pretty fun. I am excited to tell you this, though, that not only do I think this is a really good way to explain differentiability, but my man Steve does too. Isn't that wild? Like, Steve Strogatz and me, same brain, I wish. All right, anyway, in his book, Infinite Powers, I decided to, dive into that again and see, well, what did he have to say about this? And he said this is a good quote. As we zoom in closer and closer, that piece of the parabola should begin to look straighter and straighter. In the limit of infinite magnification, okay, now I have to say this word, which amounts to zooming in on an infinitesimal piece of the curve around the point of interest, that magnified piece should approach a straight line. If it does, that limiting straight line is defined as the tangent line at that point of the curve, and its slope is defined as the derivative there. Okay, he goes on to talk about the fact that, what you're doing with a derivative is you are defining a function to represent the slope of a curve. It's not just, looking at one particular point and identifying the slope of the tangent line at that particular point. A derivative is broader than that. It's saying, let's see if we can define a function that we can use to find the slope of any point along the curve. So going back to y equals x squared for a moment, I should mention that its derivative is y equals 2x. I'll put this over here. So when we have the function y equals x squared, I'm just going to use the notation y prime. That is derivative notation. What we get is 2x, and we get that from the power rule, which is something that I discuss with my students in detail after we do this little activity, but we sort of start to see it here. Okay, and so the good thing about knowing how to find a function as your derivative is you can look at that function as well to determine whether your original function is differentiable. If your derivative function has no discontinuities, if it has no restrictions, there's a bow, woo! Y equals 2x has no restrictions, right? Y prime equals 2x has no restrictions. Since it has no restrictions on 2x, that means that the function y equals x squared is differentiable everywhere. That's exciting, right? Just look at the derivative if you can, and no restrictions means it is differentiable. All right, now let's look at one that is not differentiable everywhere. The cube root of x squared, or we could also call that x to the 2/3, right? This is an example of a function that's not differentiable everywhere. Okay, I first want to show you why it's not differentiable. I'll tell you, it's at x equals 0. Okay, it's not differentiable at x equals 0, and I want to show that to you by zooming in on that point. But then I also want to show you that it's not differentiable from taking the derivative of it. Okay, actually getting the derivative equation. But first, let's do this. I'm going to go to my graph, and I am going to type in x to the 2/3 power. I like to put parentheses around that fractional power, and I'm going to hit graph. I like to call this graph the seagull graph because, sometimes you can draw seagulls in the sky as just those fancy little V's. I also call it my curly V or fancy V. All right, as I said, this is a function that's not differentiable at x equals 0. So what I'm going to do is I'm going to zoom in on the point 0, 0. And this takes a while. Usually on this calculator, it's a little bit faster, but it's not being super fast today. I wonder if I could do it on here. No, I don't know how to do it. Maybe like that. Yeah! Oh my gosh, this is exciting. So I'm going to slide this to 0, a equals 0. And watch this. Zoom in, zoom in, zoom in, zoom in, zoom in, zoom in, zoom in. Notice that I'm zooming in pretty far. That's as far as I can go on this little tool. And what you're not seeing that we saw in the last one is a line. You're not seeing a line, right? You're kind of seeing two lines here, or they're still a little bit curved. Going back to the calculator, if I keep zooming in, it's looking pretty similar, right? Yeah, and I'm not going to keep doing this to take up any more time, but I'm zoomed in a whole lot there. Look at my window. My window is very small on both axes, and I'm not seeing a line. So what that indicates to you, you could say informally indicates to you, is that this function is not differentiable at x equals 0. And the reason it's not differentiable at that point is because when we zoom in, what we're trying to do is see the line that is the tangent line that we can take the slope of. But at x equals 0, there's sort of two lines happening there, right? There's a line on this side, and then it quickly changes to, we could call this a decreasing section, and then we have this increasing section. There's a quick change there. I call it a sharp point. You can call it a quick turning point. But since a derivative is a limit of the slope, and the left and the right do not match, the left slope and the right slope do not match, that's why you cannot calculate the slope there. Okay, finally, one other thing that we can do with this one is we can take the derivative as an equation. If f of x is equal to x to the 2/3, what is f prime? Okay, well, here's what it would be. The 2/3 comes down as a coefficient in front of the x, and you subtract 1 from the power. So 2/3 minus 1, that's negative 1/3. Putting that back into radical form, that gives us 2/3 times the cube root of x. That equation has restrictions on the x, right? You cannot plug 0 in for x. You can't sub 0 in here. F prime of 0 is undefined. An undefined derivative indicates that the original function is not differentiable at that point. Okay, whoops. This would probably be a good time to talk about the word continuity as it relates to a differentiable function. Okay, so what I'd like to point out to you here is that the function f of x equals x to the 2/3, I might have lost it in my calculator. Let's see. Nope, it's still there. I'll go back to a standard viewing window. That is a continuous function, right? You can see from the graph, I guess we could say that it's a continuous function. There's no breaks in the graph. There are no holes if you examine the table. Or a better thing to say would be when you look at your function here in its equation form, you can tell that there are no restrictions on your x, right? So this is a continuous function. A continuous function can still be not differentiable at particular points. But also, if a function is not continuous, that definitely means it's not differentiable at that point. Okay, let me advance the slide so you can kind of tell what I'm talking about here, hopefully. All right, so here's some points that are not differentiable. The first one we discussed in the last example. Whenever you have a sharp turn, that's what I typically call it. Sometimes it's called a corner if it's two lines that come together. Sometimes it's called a cusp if it is curves that come together at a sharp point. Then you would say that that is not differentiable. Okay, going over here to this end, something called a vertical tangent, where your graph goes vertical at a point, or if you were to zoom in on a point, you would see a vertical line. That is not differentiable. It's not differentiable because there's another bell. Woo! I should have had like a little counter, counting how many times the bells ring. All right, anyway, a vertical line has an undefined slope, right? An example of that would be like the cube root of x. Y equals the cube root of x. If you were to zoom in on the point x equals 0, you would see a vertical line. And so we say that the cube root of x is not differentiable at x equals 0. Those two examples that are here on the left and the right, they are examples of functions that are continuous everywhere, but are not differentiable at particular points. Okay. However, also, anytime you have any sort of discontinuity, that is not differentiable either. Think about it. If you can't even have a function value at a particular point on a function, are you going to be able to calculate its slope? Okay, that wouldn't make sense. Especially with, this example, this is pretty clear. How do you calculate the slope of this jump? Well, you don't. Okay, and so what we say is that differentiability implies continuity. Okay, I'll say that again. Differentiability, meaning if something is said to be differentiable, then it is continuous. Okay. The converse is not true, however. Flip it around. If you say something is continuous, then does that mean it's differentiable? No. You can see two counterexamples to that statement right here. A corner or a cusp or a sharp point. It is continuous, but at that point it's not differentiable. A vertical tangent, a vertical, spot here on this graph, it's continuous, but it's not differentiable. Okay. I'd like to talk about now this function, but I'm getting a little bit nervous because that means I have to pronounce it. I'm pretty sure you call it, okay, breathe, the Weierstrass function. You can go ahead and make fun of me for that pronunciation. I even looked it up and practiced. Look at this. I will show you. I'm just, going to make fun of myself here. Watch this. Look, there it is. It just pops right up. It's like, yeah, you've Googled this like 7 times today. Here you go. Okay, we'll let this thing pronounce it for you as well. Weierstrass. All right, that's enough. I don't know what's going on. Anyway, this function is pretty cool because it is an example of a function that is continuous everywhere and differentiable nowhere. So, it's a perfect example, counterexample to the statement that continuity implies differentiability. No, definitely not with this one. And I just want to click on this for a moment to take you to the Wikipedia article because there's something really funny in it. I think it's funny, at least. You can decide for yourself. Whenever you start to dig into this stuff and you read the history on it, I just think it's hilarious. And what's also hilarious is it's not loading. There we go. All right, right here. This is so great. So Weierstrass's demonstration that continuity did not imply almost everywhere differentiability upended mathematics. Isn't that wild? This just upended mathematics, this function right there. Overturning several proofs that relied on a geometric intuition and vague definitions of smoothness. So we talk about a smooth curve being differentiable. These types of functions were denounced by contemporaries. I'm not going to try to pronounce that guy's name, but this guy famously described them as monsters and called Weierstrass's work an outrage against common sense. I just think that's hilarious. It's so great. All right, a little history for you there. Sorry to this guy that I didn't pronounce his name. I'm not even going to try because I'll just butcher it and get made fun of. I'm really bad at that stuff. All right. Finally, the last thing that I want to do is I want to sort of go off of that idea that differentiability implies continuity, because that is a true statement. Okay, we were just talking about how the converse is not true. To do one little example with you. Let's do some actual calculus here. The real math. What do you need to do? Let's look at this one. Suppose the function h of x is defined by h of x is equal to this piecewise function where the first piece is k times the square root of x plus 7 for the interval from 0 to 2, and the right-hand piece is mx plus 5 for the interval from 2 to 7. K and m that you see here are constants. If g is differentiable, and this is like clutch that you know what this word means for this example. If g is differentiable at x equals 2, what are the values of k and m? All right, this is super fun for me because I'm just doing this without looking at my answer key. I have no idea where my answer key is for this right now, but let's just jump in and talk about it. Okay, so The first thing that you actually should consider here is that if the function is differentiable at x equals 2, that does mean, it implies that it is continuous at x equals 2. So for a piecewise function, since 2 is a boundary point, you want to make sure that the value of the left-hand piece matches the value of the right-hand piece. We do already have our function value established with the equals here in the left-hand piece, and that will be taking care of the fact that this needs to be continuous. Okay, so the first little thing I do with this is I say I want the value of the left-hand piece when x equals 2. Notice I sub 2 in for x, to be the same as the value of the right-hand piece, again, when x is 2. So I set those equal to each other. Now, there's not much I can do here but simplify a little bit. Let's see, that's 3k. And I'll write this as 2m plus 5. And I'm just going to leave that alone. I'll do a little bit more with it in a moment. Notice I have one equation with two variables, though. So there's not much more I can do other than, move stuff around. Okay, the next part to this is knowing that not only do the function's pieces need to match at x equals 2, but also the function's slopes need to match at x equals 2. And so what we need to come up with now is the h prime of x equation, and it will also be a piecewise. All right. Now, this is something that I would typically do a lot later in a derivatives unit when students are very comfortable with taking derivatives. So, if you're not comfortable with all of this stuff, that's okay for right now. You will be able to do these pieces later. The first thing that I'm going to do is I'm just going to make a note over here that if I have x plus the square root of x plus 7, that is the same as x plus 7 raised to the half power, and I'm going to do the power rule on this piece. The 1/2 comes down as a coefficient multiplied by the k. I keep the x plus 7, but I subtract 1 from the power to get a new power of negative 1/2. Now, technically, I usually talk to my students about chain rule. Again, I would do this problem a lot later in the unit where I would, remind them that they should think about chain rule. However, even if you don't think about chain rule for this one, you're okay because you would just be multiplying by 1. And this is for the same interval. Because we know that it is continuous at x equals 2, we can include 2 in that definition. The other side is pretty easy. If you think about this, mx plus 5. Okay, m is a constant, so m is a number. Maybe m is 3, who knows? But what I'm noticing here is that this is definitely a linear piece to this function, right? It's a line. So what is the slope? Well, the slope is m, right? This is like mx plus b. It even has the perfect letter with it, m. So the derivative on this side is just m. And again, we can say for the same interval. All right, now that we have our derivative equation, we want these pieces to match when x equals 2. So I'm going to set up something similar to this. I'm going to say when I take the left-hand slope at x equals 2, so notice I'm subbing 2 in for the x, I want it to match this piece. Now there's no x in this piece, so we just carry down the m. Simplifying this a little bit, let's see, 2 plus 7 is 9. This would be a square root in the denominator, so that's a third. So this is 1/6, k equals m. Now, what I love about this problem, I don't know, whenever I see these, I'm like, these are fun. They're like little puzzle pieces, is that now you take the pieces that we have over here and you put it together with the pieces that we have over here. We have just created a system of equations that we can solve, I would say, through substitution, because we know that m equals a 6th k. We can sub that in right there, right? And we can write that as 3k equals 2 times a 6th k plus 5. And solve for k. Subtracting the 1/3 k. I'm going to move my work over here. Sorry about that. Let's see. What's that? 8/3 k. This is where like my anxiety is kicking in. I'm like, why don't you have your answer key with you? What is wrong with you? Okay, and I believe that will work out to be k equals 15/8. And now my brain's saying, yeah, that sort of seems like the right answer, because I do have an answer key somewhere that tells me the correct answer to this. Let's just go with it. Now that we found k is equal to 15/8, I had to go away so that I can fit the rest of this and you can actually see it. The last little bit, I have so many arrows. I'm sorry. Sometimes I joke that my work looks like a football playbook. Not that I know anything about football, but I don't know. Seems like it would. All right, anyway, the last little bit of this is that we need to calculate m. M is 1/6 times the k value. And let's see, when we do that multiplication, we get 5/16, right? That sounds good to me. Now what I'm going to do is run to find my answer key and check it to be sure I'm right. But I feel good about it, and I think you should feel good about it. And I will come back to you for a moment. I really hope this was helpful, and good luck in the rest of your studies. Bye.